Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about a very classical application of Galois theory to the constructibility of regular n-gons via ruler and compass constructions. So let's just start by reviewing what is involved with a ruler and compass construction. So what do I mean by ruler compass construction? So this is something that is classically taught in field theory courses, so hopefully you've seen this before, but if not, I'll review it very quickly. Okay, so how does this ruler compass construction work? So what we'll do is we'll start with just 2 points and I'll mark them inside the complex plane as 0 and 1. That's going to be my seed. And I'm going to play this ruler compass game, which is basically trying to abstract what you can draw when you use a ruler and a compass. So what types of things can you draw? So what we're going to do is we're going to have this finite set of points, and given this finite set of points, what I'll do is I'll draw all the lines through any two points there. So there's only 2 points there, so there's a single line here, which will be the real line here. And the other thing that I can do is I can draw any circle with center, one of the points that I have here, and also whose radius is the length, which is the distance between 2 points inside here. So I can draw a circle with center 0 and whose radius is the distance between there, that's 1, so that gives me a circle like this. And I can also draw a similar circle with center 1 and radius 1. Okay. And what happens now is that I'm going to look at all the intersection points of all the lines and circles that I have here. So of course with this, I'll also have -1 over here. Okay, I'll have 2 over here. And more interestingly here, what I'll have is e to the 2 pi I on 6. And similarly over here, I'll have e to the minus 2 pi I on 6. Okay. And then I can repeat this procedure. Okay, so what I'll do is I'll look at all the intersection points, which will now also include this one, this one, this one, and this one. I can look at any pair of points, and I can draw a line through them. I can look at any point and draw a circle with that center and whose radius is given by the distance between any 2 points. So those points might include that original one, but it could be 2 completely different ones. Okay, and then I'll get a bigger configuration of lines and circles, and I can look at all the intersection points and so forth. And eventually, you'll draw lots of things, lots of figures can be drawn as a result. Okay. So the definition I want to introduce, which is the most convenient to describe the mathematical results involved, is the following. We'll say a complex number z is constructible if it arises as an intersection point in this ruler compass game. Okay, so the constructible numbers that we see here are -1, 0, 1, 2, e to the 2 pi I on 6, and e to the minus 2 pi I on 6 here. But of course, there'll be infinitely many as we are allowed to play this game indefinitely. Okay, so this is the type of game that you use to describe the fact that you can't trisect an angle with a ruler and compass. Okay, so that's something that you may well have seen in a field theory course. Okay, so let's just move on and talk about the criterion for constructibility, okay, which is rather nice. It's a simple mathematical criterion. And it uses the following proposition, and I'll also give a definition associated with this. So suppose you have a field extension k over f, we're going to call it, and this is a non-standard definition, a quadratic tower extension. I'll abbreviate this to QTE. If there exists intermediate fields between k and this f, they're going to be intermediate fields f1, f2 up to fn minus 1, okay, such that they sit in this chain, and the index of each field in the next one is going to be 2. Okay. Well, occasionally maybe we allow also equality, so it also can equal 1. Okay, that's not going to change this definition. Okay, so basically you have this sequence of subfields, okay, of intermediate fields, and such that each field is indexed 2 in the next one. Okay. And one of the things that we can say about this quadratic tower extension, like the existence of this filtration here with this condition here, means that you can say something about the degree of k over f. Okay, what's the degree? Okay, and the degree of k over f, so it's basically the product of all these degrees, and all these degrees are 2 or 1, so basically this is a power of 2. So if you have a quadratic tower extension, then the degree of this extension is some power of 2. Okay, so let's have a look at a simple example. Okay, so the example I want to have a look at, which will be important for regular pentagons, is the following. Suppose you look at zeta is the primitive fifth root of unity here, e to the 2 pi I on 5, and you look at q adjoin that. So inside there, of course, you can look at q adjoin, you can look at q adjoin zeta plus zeta inverse. So this is certainly inside there, so this will be a subfield. Of course, zeta plus zeta inverse is just 2 cos 2 pi on 5. Okay, and we know this is not a rational number, so this also contains q. Actually, you have strict inequality here. This includes some non-real numbers. This is real. Okay, so we can actually see that this is non-trivial. And of course, this is not rational, so you'd have inequality here as well. So there's a strict inclusion here. Okay, so I claim that this shows that this here is a quadratic tower extension of Q. Okay, it's quite easy to see why. So what's the degree of this over this? Okay, it's actually 4. This is something that we saw before. Okay, this cyclotomic extension. Okay, you're joining a primitive fifth root of unity. In fact, the minimal polynomial of this over Q is just x to the 4th plus x cubed plus x squared plus x plus 1. So that gives you the degree of this is 4. And we've split this up so that this is degree 2 and this is degree 2. Okay, so the degree of this is the product of the degrees of these two. And of course, this is non-trivial factorization of 4. So it's 2 and 2 here. And that gives you a quadratic tower extension. So hopefully a theorem that you've seen, I'll briefly state why it's true anyway, is this following very nice criteria for when complex number z is constructible. And it's constructible if and only if you can find some quadratic tower extension k of q such that z is inside this quadratic tower extension. Okay, so let's have a look here and see what happens. So firstly, let's look at the constructible numbers that you see here. Okay, so the ones minus 1, 0, 1, 2, they're all rational, certainly. And so they're constructible according to this. And we can see they're constructible. The two more interesting ones are these two here. Okay, e to the 2 pi r and 6 and e to the minus 2 pi r and 6. And certainly you can get them by adjoining a root of a quadratic equation, so by adjoining square roots. Okay, so that's quite easy to see if you expand this out. Okay, into the real and imaginary parts. Okay, so if you haven't seen this before, let me just briefly explain why this is quite a natural sort of condition to come up with. So I want to suggest how the proof goes. The proof is actually long. It uses a lot of case-by-case analysis, but these are the following ideas. So firstly, we're going to look at the set of all these constructible complex numbers, and we'll call that C. C is the set of all these constructible complex numbers. And let's make some simple observations about this. So firstly, Z inside C, okay, it's constructible if and only if the real part and the imaginary part are also constructible. Okay, so why is that the case? So let's just think briefly. If you have some complex number, suppose it's sitting up like this, okay, you can use a ruler and compass to drop a perpendicular onto the real axis and onto the imaginary axis, okay, and hence construct them. They'll occur in this ruler compass game if that complex number was constructible. Similarly, if you have these two are constructible, Okay, well I guess technically they both sit on the real line, but it's easy to draw a circle and then rotate onto the perpendicular going through 0 to get the imaginary point, the imaginary part on the imaginary axis also as constructible, and then you can use perpendiculars going out this and like this to get you the complex number if you know that the real and the imaginary parts are constructible. Okay, so this means that to a certain extent you can turn this into a real problem, and that's how often this is done. So the key point is that why is it in this condition, okay, that you're always just looking at degree 2 extensions? And the reason is very, very simple, and this is the key point, okay? When you want to try to work out these intersection points, you're just solving equations, and what are the equations of? The equations of lines and circles. Lines are defined by linear equations, okay? And the coefficients of those equations will depend on the points that they go through, okay? And in particular, if they go through points like rational points, like 0 and 1 or whatever, then this line will have the defining equation you can pick to have rational coefficients, okay? So the circles, similarly, okay, you can define these circles using quadratic equations. And where do the coefficients come from? The coefficients come from the points that are used to define that. Okay, so if they come from a particular field, they kind of stay in that particular field. Okay, and of course, when you're solving linear and quadratic equations, okay, and the coefficients come from a certain field, essentially the only thing that you can do is to join, is make a degree 2 extension, okay, as in the solution set. Okay, so that's kind of the key point as to what's going on. So, so that's 2 important observations about C itself. The next 2 are also quite important, but maybe are motivated from this point of view. Okay, so let's have a look on the other side. Okay, what are all the points, all the complex numbers Z which lie in some quadratic tower extension? Well, one way to think about that is that if you look at the set of all these points that live in some quadratic tower extension, this is closed under certainly all the field operations, because if you lie inside here, you do some field operations with these, you have some elements that lie inside here, you can add them together, they'll stay inside here, multiply them and so forth. And also you can take square roots in this set, okay? If you look at the set of all of these, you take a square root, then maybe you won't stay inside here, but you'll stay inside some bigger quadratic tower extension where you've extended this by some square root, okay? So this set is going to be closed under field operations and square roots, okay? And in fact, it's the smallest subset of the complex numbers which contains Q, okay, and is closed under the field operations and the square root. Okay, that's one way to describe it. And the point is that exactly the same is true of C. And this takes a little bit, this is where there's a lot of case-by-case analysis, okay? So this set C is actually closed under all the field operations, okay? And also under the square root. And C is the smallest such thing, okay? So that allows you to identify these 2 sets, the set of constructible numbers and this set of numbers which lie in all possible quadratic tower extensions, okay? And this is the bit where it's kind of a little bit tricky to kind of see why that's true, and you have to go through each of the operations, okay, in turn, and actually do some constructions. But let's just see some simple things. So for example, if I want to say, well, why is 1 plus 1 inside the set of constructible numbers? Remember, we started with 0 and 1. Well, to get 1 plus 1, we'll put down the 1 here, we drew this circle, okay, which adds in this 1 to this 1, and that's how you get 2, okay? So similarly, you can try to figure out how you can construct the minus, the times, the divide, and also square roots, okay? So of course, square roots is where you need to intersect at least a circle with lines, okay? So the other operations, I guess you can do mainly with lines. You might need to use circles a little bit, but it's mainly linear operations. Okay, so that's a summary of the field theory that we will need to talk about ruler compass constructions and how to identify what you can construct with a ruler and compass. So next what I want to do now is to look at the special case of a regular n-gon. Okay, so the question here is basically, can you construct a regular n-gon? So an example that you should know is that you can easily construct a regular hexagon, okay, with a ruler and compass. And so I guess what that means is that if you play this ruler and compass game, okay, you will eventually get lots of lines and circles, and all the lines giving you this regular hexagon will appear. Okay, so that's something that you can see. And an equivalent way of stating this, because we didn't define constructibility for figures such as the hexagon or the regular n-gon, the way we want to say it is just that constructibility of the regular n-gon just means constructibility of this complex number e to the 2 pi I on n. Okay, so my theorem here is going to be talking about when is this e to the 2 pi I on n, and hence the regular n-gon, constructible. Okay, so this, when is this a constructible number? And the criterion is very, very simple. Okay, the criterion is it's if and only if the Euler phi function of n is a power of 2, because power of 2 is what you see here. Okay, so what is this Euler phi function? Let's just remember. One way to think about it is that you look at this ring Z1 n, you look at the units in there, and it's just the number of elements inside that. Okay, so let's just have a little play around with this theorem and make sure that we understand properly, and see that it works in this very special case here. So we know we can construct a regular hexagon. So this theorem is telling us that the Euler phi function of 6 ought to be a power of 2. So let's see what this phi of 6 is equal to. So that's just the, you look at Z1 6, the units in there, and you count the number of elements inside there. So what are the units inside there? So you're looking at Z1 6, so I guess you have 1 plus 6Z, that's the unit, okay. 2 is not relative prime to 6, neither is 3, neither is 4, but 5 is, so that's the only other element. That's the other element. And so there are only 2 elements in there, so that's 2. That's a power of 2, and so that we know, without having to do any actual ruler compass constructions, that the regular hexagon is constructible by ruler and compass. Okay, let's have a look at some other examples. So the regular 5-gon. So phi of 5, so this is a prime number, so that's just 5 minus 1 is 4. That's a power of 2, so this is constructible. And here we have the quadratic tower extension, okay, for this q adjoint e to the 2 pi I on 5, okay? So that's constructible. 17 gons, okay, what's phi of 17? Phi of 17, so this is prime, so that's just 17 minus 1 is 16, that's a power of 2, and so that's also constructible. So these two are constructible. And while this rule and compass construction of the 17 gon, it's quite an exercise to try to do the actual rule and compass construction of it, was something that Gauss famously did. Okay, so I want to give you a proof of this theorem, which is rather nice, and it uses Galois theory. Okay, so the first bit doesn't really use Galois theory, okay, which is in this direction here. So let me tell you about that. That's quite easy. So suppose you look at this nth root of unity. We'll call it zeta n to simplify notation, e to the 2 pi I on n. And suppose that it lies in some quadratic tower extension k of q. Okay, so by this criterion, that's what constructibility means. It lies in some quadratic tower extension. And we just have to show that this phi of n is a power of 2. So let's see how that works. So we look at phi of n. Definition is just the number of elements in the unit ring or unit group of z mod n. And remember what this is. So this z mod n cross, okay, is also just the Galois group. Okay, we saw this is the Galois group of q zeta n over q. So I guess it does use some Galois. Okay. So that's the Galois group. I'll later call this G of q zeta n over q. We're looking at the Galois group this field extension. Okay, and since you have that, the order of this Galois group, okay, is going to be what? So this is a Galois extension, and the order of that Galois group is just the degree of the field extension. Now, you know, we haven't used the assumptions here yet, right? So the assumption is that, well, this zeta n is inside some k. So this q zeta n is contained in some k. So you have a power of field extensions, k contains that, contains that. So the degree of k over q is the degree of k over q zeta n times this here. Which means that you can rewrite this as just a quotient. It's just the degree of k over q divided by the degree of k over q zeta n. And the key point, remember in this proposition definition, you want to use that fact that this is a quadratic tower extension of q, so this degree is a power of 2. So you just have a factor of power of 2, which is a power of 2. Rather nice, isn't it? Okay, how this works out. Okay, let's go in the other direction. Let's prove the other direction. So the other direction, going back, is you're going to assume that this Euler phi function of n is going to be a power of 2, so 2 to the n. Okay, and remember what this is. We saw before how this works is if we let g equal to, so from this equation here, this phi of n you can also write as just the order of this Galois group, which I've denoted by g. Okay. So this Galois group, remember, is this group here, this unit group, and in particular it's a commutative group, it's abelian. So you can now write this as a direct sum of cyclic groups, and each of these cyclic groups has the form z mod 2 to the some power. Okay, so that's just some abelian group theory, and from this it's quite easy exercise to show that you can construct a sequence of subgroups starting from 1, okay, the trivial subgroup, all the way up to Gn. It's a sequence of subgroups such that the index of 1 in the next one is always 2. In fact, this is quite true generally of any group G. If it has an order which is a power of 2, you can always do that. Okay, it's an nilpotent group, you can always do that. But if you don't know this fact, okay, which is not that difficult actually, but if you don't know this fact, you just use the fact that, well, G here is also abelian, and so we have more structure that we know about it. It has this form, it's a direct sum of cyclic groups, and then it's quite easy to actually do this construction. Okay, so in many ways to find the sequence, it really reduces to each of the summons, okay, because you just want to make it bigger. So if we can make it so we can start the filtration by saying, oh, you put this one here, and then this one directs on this one as the next one, and so forth, and then you have to fill in those the filtration with more groups, and that reduces to the case where you have a single cyclic group. And so, for example, if you have Z mod 4, okay, you can always insert, for example, in Z mod 4, you can insert the group generated by 2, which will be which will break it up into this form. Okay, but I'll let you think about how that's true. And now this is kind of the point about, you know, the Galois correspondence. How do you use the Galois correspondence? And this is a classical way where you can actually use the Galois correspondence. Okay, so the Galois correspondence tells you that the lattice of subgroups of the Galois group corresponds, reversing inclusions, to the lattice of intermediate fields. So what you can do is you can use the Galois correspondence. Let's remind ourselves how that works. Okay, so the Galois correspondence means that to each of these groups, okay, subgroups, you can look at the corresponding fixed field, Ki. And this reverses inclusion. So G0 goes to K0, so what's fixed by 1, of course, is everything, so that's the whole field. What's fixed by G1, that's going to be some K1, and that's going to have, this is going to be degree 2 over that, because that's the index of this group inside here. And so forth. What you end up is you'll get a chain of fields. Okay, so this reverses all those inclusions. You get a chain of fields like this, going all the way down to Km. What's fixed by G is the Galois extension, so this is going to be Q. Okay, so you've got this chain of intermediate fields. And because all these indices are 2 successive subgroups, that means the degrees of the successive fields is also 2. So you get a quadratic tower extension. And that completes the proof of this wonderful theorem, which very simply characterizes which regular n-gons can be constructed by rule and compass. I hope you enjoyed this adventure in pure mathematics.